Hello, everyone. Welcome to this week's seminar. Today we have Bernard Bainson from the Kwame Nkrumah University of Science and Technology, Ghana, speaking to us on the topic extensions of ordered groupoids. So welcome, Bernard, and you can present your work.
Oh, thank you, Angela, and thanks to the organizers for giving me the invite and the opportunity to put across the research that I do. So this work on extensions of ordered groupoids was done together with Nick Gilbert from Herod-Watts University. So he was my PhD supervisor, and these are some of the things that we had a look at during my training. So basically in mathematics, most of the time we do consider spaces, and then what we do is to look at how we can move from one space into another space. In particular, we want to look at extending smaller spaces into bigger ones, and the ways in which we do it are so many. Typically, we can look at embeddings, where the smaller space can be embedded into the bigger one. Or we can also look at coverings, where we see that we have a map from the bigger space into the smaller space. And these kinds of maps between these spaces helps us to uncover so many properties and other beautiful things that can be found within these spaces. In particular, if it turns out that both an embedding and then a covering exist in a particular field, then we say that the two sequences that we have there, the embedding sequence and the covering sequence, is split. In practice, we may not have both concepts appearing, because sometimes some of these concepts are trivial, and so we don't really consider them that much. For groups, we are much interested in coverings, because it turns out that if you have a covering, it's able to generate an embedding. And so considering coverings is sufficient, because we can tend to have the notion of embeddings being considered thereafter, because these are going to be generated. So for example, if you have a covering from Y into X, it's mostly just a surjective map. And so you can find the kernel of that surjective map, and then this put together can give us a short exact sequence of this form. So if A is a kernel of the surjective map from G into Q, giving us pi, then if we say that A is a kernel of the map pi, then we can embed A into G, and then we have our surjective map from G into Q. So we notice that this map here is exact, because if we take any of the maps, we notice that the kernel of a map is equal to the image of the previous map. So the kernel of pi is the image of I in this case. And since this happens, we say that that sequence is a short exact sequence. And it is these kind of sequences that we will be calling extensions. And so we will say that G is an extension of A by Q. G is an extension of A by Q. And so a formal definition would be an extension of a group A by a group Q is a short exact sequence from A into G into Q. And the consequence is the following. We can see that G will contain a subgroup that is isomorphic to A. And I'm not sure how many of us are familiar with this notion of groups and subgroups and etc. But if not, we can still ask them, probably during the discussion or in a course of my talk. So G turns out to have a normal subgroup that is going to be isomorphic to A, and then the quotient of G by A is going to be isomorphic to Q. Depending on the properties of A, we may call our extension by different forms. So we can say that we have an abelian extension when A turns out to be an abelian group. So depending on what properties you have of A, we may call the extension by different names. And in particular, we will be interested in ones where this group here is abelian. So we might say extensions of groups with abelian kerf. So group extensions do exist. We can give several examples. So for example, if you have any group homomorphism, G into gamma, then we'll be able to find a group extension out of this. And the immediate thing to do is to look at the image of pi. And so that we can say that we have a surjective map from G into pi G. And then the kernel of that map will be what will sit at the bottom there. And so this sequence here is exact, and it's a short exact sequence. So we can say that G is an extension of kernel of pi by pi G. And we can give so many concrete examples. And this is what we are interested in, finding extensions. The question that is mostly asked is, knowing the group that sits here and the group that sits there, we can identify several groups that can fit into this spot. Now, if you identify those groups, what is going to be the relation between them? If you have two different groups, G and G prime, that sits here, it may turn out that occasionally those groups may be isomorphic or they may not be. And so if that is the case, then we could possibly have equivalent classes of these kinds of extensions. So what we want to do, which is a big question that is being considered when we look at extensions of groups in particular, is to look at how to classify all the extensions that we may have. So this is in terms of groups. So relative to this, several people have made remarkable contributions. We can think of Schrey in 1926, by Barr in 1934, Turing, Ellenberg, and then MacLean. The one that I have highlighted in black is where my motivation is from. So the extensions of ordered groupoids that we considered, our main motivation comes from the account by Carl Grunberg. So that is why I've highlighted that in black. So all of these researchers have made remarkable contributions that has gotten the extension problem to its current status as we have. The good news is that for inverse semigroups, which are supposed to be the algebraic structure that is closely related to ordered groupoids that I considered, MacLean and Ellenberg identified the extensions for groups can be classified using the second cohomology group by what we mostly call the factor sets. But then that of ordered groupoids, that of inverse semigroups was not considered for quite some time. And so it was later on that we got some breakthroughs. And that's where I'll be taking my discussion from. Grunberg has also given a conceptual discussion of extensions of ordered groupoids, which doesn't use the notion of factor sets. It's a very beautiful construction. And so that is where I take my inspiration from. And that's where all the computations that I did with Nick Gilbert, that's where it comes from. So we will see it later on. So for inverse semigroups, the paper that motivated what our discussion was that of Lausch. So he developed an extension theory for inverse semigroups using the cohomology of inverse semigroups. He used the factor set approach, and that is not what I will be using. What I'll be using is essentially an account by Loganathan which uses the cohomology theory of categories. So there is inverse semigroups, there's the cohomology of inverse semigroups, and then Lausch just did as was done by MacLean and Lindbergh to use a factor set approach. But then Loganathan also later gave a different account based on what Lausch has done, but then using the cohomology of categories. So out of the inverse semigroups, he built a category and then used the cohomology of that category to classify all the equivalent classes of extensions of inverse semigroups. So this is our motivation to use Loganathan's account and that of Greenberg to develop one for ordered groupoids. I have mentioned groups, ordered groupoids, inverse semigroups, etc. Perhaps it is time that we can have a look at what ordered groupoids are and what we mean by the extensions, what we mean by the cohomology of ordered groupoids. So this is what we are going to do. I'm going to describe what ordered groupoids are, what we mean by extensions of ordered groupoids, what we mean by cohomology of ordered groupoids, and then use the cohomology of ordered groupoids to classify extensions of ordered groupoids. So our goal is to classify extensions. And to do that, what I'm going to do is to use the notion of cohomology of ordered groupoids to classify that. So we will first describe what ordered groupoids are so that we get to know the structure that we are dealing with, and then note what extensions are. And based on that, we can classify using the notion of cohomology of ordered groupoids. So I'm believing that we are good to go now. Okay, so first of all, in the name ordered groupoids, we see the word groupoid. So we have to understand what we mean by groupoid. And then later on, we can add the adjective ordered, and then we can get the full meaning of what we mean by ordered groupoids. So a groupoid is a small category in which every morphism is invertible. If you have never heard of a category before, it is just a system that contains identities and maps between the identities. And these maps should, of course, be nice enough. We should be able to compose where possible. The composition should be associative. We should have identity morphisms on the identities that we have. We can read more about category theory if we are not so much in tune with that from, I think, a basic introduction would be that of Tom Lester. So you can look it up from there. So a groupoid is any small category in which every morphism is invertible. So we have a set of identities and then you have morphisms within it. And then we are saying that if you pick any morphism, you should be able to find an inverse morphism in this category. So a typical example is the notion of groups. So we can say that a group is a groupoid because in the group we have one identity, which is the E, and then every morphism has an inverse. So a group can be considered as a category, as a groupoid. Now we throw in the orderedness and then say that an ordered groupoid is a pair, G and then less than or equal to. So G is a groupoid, and then the less than or equal to is the partial order that is defined on G. So it's partial, that means that it is not every pair of elements within G that can be compared using that order relation. So some elements are comparable, others are not. So the pair G and the partial order will be called an ordered groupoid, provided that it satisfies the following conditions. So if X is less than or equal to Y, then this implies that X inverse will also be less than or equal to Y inverse for all X and Y in G. Again, if you have X, Y, U, V in G, such that X is less than Y and U is less than V, then U, V, U, XU should be less than or equal to YV whenever XU and then YV exists. So it is not all the time that we are able to compose morphisms within G. And so if XU and YV do not exist, then this wouldn't happen. But once they do exist, then XU should be less than or equal to YV. And the next thing we can say is that if you have a morphism X in G and an identity E, so we would denote the set of identities of our ordered groupoid by G0. So we say that if X is a morphism in G and then E is an identity in G0, then we will say that given that E is less than or equal to the domain, so I'm using the bold font D for the domain. So if E is less than or equal to the domain of X, then we'll be able to find a unique element which we will call the restriction of X to E, such that the domain of this restriction is E, and then this restriction is less than or equal to our morphism X. So it's like you have a morphism X that sits up there, and then you have an identity E that sits at a point below the domain of X. So you should be able to find a unique morphism, which we are calling the restriction, that will start from E, and then this morphism is below X. So it's going to be less than or equal to X. Based on condition 1 and condition 3, we could also say that whenever E is less than or equal to the range of X, we should be able to find a unique morphism. This time around, we won't call it a restriction, but rather the co-restriction of X to E, so that the range of this morphism is E, and then this morphism is less than or equal to X. So any groupoid together with this natural partial order that satisfies this condition will be classified as an ordered groupoid. Immediately, we can say that every group is an ordered groupoid. The partial order there is just the equality. Apart from that, we can also say that any partially ordered set, coset P, can also be considered as an ordered groupoid. So the ordering is coming from the partial order within your coset. If you have a group homomorphism from a group K into a group H, then we can get an ordered groupoid from this structure. The object in this case will be the identities in K and in H, and then the morphisms are the disjoint union of morphisms within K and H. And the order that we will have is that we will say that K is less than or equal to H, provided that the image of K is H. And if you go through a verification, a simple verification, you will notice that all these conditions will be satisfied. So ordered groupoids arise in practice, and it's in line that we are looking at the extensions of these classes of objects. So to describe the extensions, we said we would need the notion of cohomology of ordered groupoids. But our main motivation was to use the account by Loganathan and then the account by Grunberg. So what Loganathan did was to use the cohomology of categories to describe the extensions of inverse semigroups. So he built a category out of the inverse semigroups and then used the cohomology of categories to describe the extension. So what we want to do is to mimic that situation and then build a category out of our ordered groupoid and then use the notion of cohomology of categories to also describe the extensions of ordered groupoids. So to build Loganathan's category, we define the following product. We call it a pseudo product. So if you have two morphisms, G and H in G, then the pseudo product of G and H, which we write as G star H, will be defined given that you have an object E that is less than or equals to the range of G and then less than or equals to the domain of H. So that the composite or the pseudo product of G and H will be the composite of the co-restriction of G to E composed with the restriction of H to E. So the pseudo product of G and H will be this morphism that we have on the next row. That is the restriction of the co-restriction of G to E and then the restriction of H to E composed. So with this product, what we notice is that whenever G star H star I and then G star H star I are defined, these two guys are equal. And this was proven by Lawson in 1998 in his book on inverse semigroups. So you can have a look at that and get more other information. So with this, we build Loganathan's category as follows. So given an ordered groupoid G, this category will have objects which is the same as the objects of G, but then the morphisms are no more going to be just the morphisms in G, but they're going to be pairs, e.g., where E is an object and then G is a morphism in G, such that the domain of G is less than or equals to E. So E is a point that sits somewhere up, and then G is a morphism that sits below E, such that the domain of G is less than or equal to E. So this morphism will have domain E, and then it will have the range of G. So in particular, if you have two morphisms, EG and then FG, then their composite will be E, G star H. So this is our E, this is our G, and then this is our F, and then this is our H. So this composition is going to be defined provided that the range of this is the domain of this map. Otherwise, we cannot do the composition. And when this happens that we can do the composition, then the composite will be the morphism from E up to the domain of the co-restriction of G to the domain of H. So that we will have a morphism that sits below here, and which is the co-restriction of G to the domain of H composed with H. So that is what we have here, the co-restriction of G to the domain of H composed with H, and then we have E as a starting point. So with this category, we can use the notion of cohomology of categories to describe the cohomology of this category, which is also the same as the cohomology of the ordered groupoid, and then use that to describe the extensions of the ordered groupoid. So what do we mean by an extension of an ordered groupoid? So we say that if Q is an ordered groupoid, and then N is a union of groups. If it's a union of groups, then that's also an ordered groupoid, because we have identities there, and within every identity we have a group there. So that group also has invertible morphisms in there, and all the conditions that we need to be satisfied. This is a disjoint union, and so no two elements within different groups are comparable, and so that's also allowed. So we say that an extension of N by Q is an ordered groupoid G, together with an ordered embedding from N into G, and an identity separating surjective ordered functor. So we expect that all our maps will respect the order. So that's why we have the ordered here. So we have an identity separating ordered functor from G into Q, so that the kernel of phi is N. So that the kernel of phi is N. So again, a consequence of this is that we have an ordered embedding N into G, and then we have an identity separating surjective map from G into Q. In fact, when this happens, this tells us that if we know a little bit of group theory, we can know that Q can act on N via the map phi. N is a normal ordered subgroupoid of G, as we note, and then there is an isomorphism from the quotient of G by N into Q. So this is what we mean by an extension. So what we want to do is to transfer the extension problem that we had in groups into ordered groupoids. So that means if you have another group G prime that can sit at this point, can we define an ordered functor between them? Is it going to be an isomorphism? If it is, then that means you're going to have some certain classes of extensions of ordered groupoids. Can we classify all of these? And so to classify that, what we also need is the notion of the cohomology of ordered groupoids. The most subtle thing is that we have to modify the cohomology theory a little bit to be able to accommodate the extra structures that has been placed on ordered groupoids, which are not present in a general group. So this is what we mean. to talk about the cohomology, some of the ingredients that we need is a module. So we will say that a module over an ordered groupoid G, which we will denote by the curly A, is the following. It's just an ordered functor from G into the category of abelian groups. So what this means is that we take an ordered groupoid, and then what this module does is to associate the identities that you have in your ordered groupoid, some abelian groups. So for every identity, you associated an abelian group AE. And then whenever you have a map between two identities, you'll be able to have a group homomorphism. So if you take the morphism EG in our category LG, you'll be able to associate it a group homomorphism from AE into the range of G. So the abelian group associated to the range of G. So this map is actually a composite. We have one from AE into A, the domain of G, and then composed with the abelian group associated with the domain of G to the abelian group associated to the range of G. So a module over an ordered groupoid is essentially an ordered functor from our LG into the category of abelian groups. So we sprinkle abelian groups over the identities, and then whenever you have a map, what you get is a group homomorphism between them. So that is what a module does. So the collection of all G modules and then maps between G modules, we will call that the category mode LG. Now, typical examples of modules over ordered groupoids are the following. I mean, these ones I am listing because we are going to make use of them. And although they may look trivial, they are very interesting and have rich information. So delta Z is the G module that associates every identity in G, the abelian group Z, and then every morphism, just the identity morphisms. So what you have is just Z sitting at all the identities, and then the maps between them is just the identities. So this module is what we call the trivial module, that's delta Z. Aside this one, we can also define the adjoint module ZG that will associate the free abelian group on all morphisms that end with target E to the identity E. So if you pick any identity E, the abelian group that will be associated to that will be the free abelian group on morphisms that end at E. Now we can define a map from ZG into delta Z. So this map will just forget we'll just sum the integral coefficient of our element in the free abelian group. And so that will give us an element in delta Z. And the kernel of this map, we will call that the augmentation module. So we denote by IG. In fact, this map here is an epimorphism. And so these three guys, modules, we are going to make use of them to define the cohomology of ordered groupoids and all the other derivations that we are going to need. Okay, so it is clear that if you have a map from G into H, an ordered morphism, then any G module will also be an H module via the action. Sorry, any H module A is also a G module via the ordered morphism tab. The action will be defined in that case. So the cohomology of ordered groupoids that we are going to use to describe the extensions will be made clear by introducing an extra identity into our category LG. This construction doesn't happen for groups, but for inverse semigroups, this was a kind of modification that had to be done to be able to accommodate the explanation that comes up. And it turns out that we had to do the same thing, a similar thing for ordered groupoids. And to be able to capture the notion of extensions. So given an ordered groupoid G, we can introduce an extra identity I and then say that I is bigger than or equal to every other identity within G. And so a module associated with G, which is the same as a module over LG, can be extended into a module AI. So what this one does is that it associates everything in GI, the module AE, if E is not equal to I, but then at I, it associates the module, the co-limits. So there's supposed to be the co-limit. So we should have an arrow underneath the limit sign from under the limit. So this was a typo. So it associates the co-limits of all the modules, all the abelian groups associated with the identities that we have there. So that's why we are summing over all the identities that we have. So in this module, it is this module that we are going to make use of to describe the cohomology of the ordered groupoids that will be needed to identify or classify the extensions that we have. And we will see this subsequently. So if we have an LG module A, then this is how we define the cohomology of the ordered groupoid. So the cohomology of the ordered groupoid G is defined as this X group. So it is given as the X of delta Z into A. And we can compute this X group using a projective resolution of our delta Z. So P here is a projective resolution. And so we look at maps from these projective resolutions into A and then compute the cohomology of that. And what we get is what we are calling the cohomology of our ordered groupoids. The notion of the X groups, I think if you can find more information about this from the book by, let's see, I think you can use the one by Hilton and Stambach on homological algebra. You can get more information there. So the cohomology of your G with coefficients in A is just the X group delta Z into A. And you can compute this using projective resolutions. And immediate results that we can get from this X group is that if your module A is injective, then the cohomology will vanish for n bigger than or equal to 0. And the cohomology at 0 will just be the limit, the co-limit of A over LG. So it is this definition of cohomology that we are going to make use of, together with a modification to describe the extensions. Immediate results that we get is the following: that the cohomology, the X group KGI into A0 is the same as the X group KG into A. So the A0 will be the module over the group GI. And then what it does is that instead of associating the extra identity element I, the abelian group, the co-limit, it rather associates it with the trivial module. So that's why we have the 0 there. And then the KGI will be the augmentation module for the GI. So the augmentation module we saw earlier on, which is the kernel of this map, that is the kernel of that map there. So in this case, we have a GI, and so our kernel will be the KGI. So we have these isomorphisms, and so we will make use of these to have some substitutions within our sequences to be able to tell of the cohomology of our ordered groupoid with the extra identity included. So one result that we obtained was that if you have an extension A into G into phi, then we'll be able to develop or generate this sequence of Q modules. So we have A made abelian, map from A made abelian into the derived model over phi into the augmentation ideal. And this sequence here is exact. You can find the proof of this in the paper that we put out there, extensions and cohomology of ordered groupoids. So based on this, we developed a parallel construction that we have in group theory, the 5-term exact sequences for groups. We developed one for ordered groupoids, and this is the most interesting result for me that we had. It's the main machinery or the main tool that we used to describe the extensions. So we say that given an extension epsilon, where n is a union of groups, and then mu embeds, so this should be n, mu embeds n into G, and then Q is isomorphic to the quotient of G by n. Suppose that A is a Q module, then we be able to find a 5-term exact sequence. So it is from this exact sequence that we are able to classify all extensions. So that is why I have this portion in blue. So what we are going to do is to use this component here to describe all possible extensions. And so that the map from this object into this cohomology group will then be an isomorphism. But to be an isomorphism, this guy here has to be trivial, and then the co-kernel of this map should force this to be an isomorphism. So what we have to do now is to identify this object here with all equivalent classes of extensions. And if you're able to do that, then we can say that the set of equivalent classes of extensions of ordered groupoids is in one-to-one correspondence with the second cohomology group. So you notice that in this theorem, the objects that we have here, the second cohomology, is not just the second cohomology of Q with coefficient in A, but rather the second cohomology of Q with an extra identity with coefficient in the corresponding module. And the corresponding module has the trivial abelian group identified with the extra identity there. It is this thing here that is not easily seen for groups, but for inverse semigroups, there is a similar construction. The proof is again in the paper. You can read it out. It has quite a rich amount of homological algebra being applied there. But because I did not know much of the audience, I didn't want to put too much technicalities here. But then we can identify this with the use of all the identifications that we have had at this point. So this is what we want to do to identify this object here with a set of equivalent classes of extensions of ordered groupoids. So how do we identify this with extensions? I mean, you have morphisms, or you have maps from N into A. N is supposed to be the ordered groupoid that will sit at the bottom of our extension, and then A is just a Q module. So we want a map from NA, B into Q, but since we are looking at N being a union of groups, it turns out that N is going to be abelian. So N made abelian is just an abuse of notation anyway. So N, we want maps from N into A, but we want these maps to respect the Q module structure. So it is not just any map at all, but maps that respect the Q module structure. So this is how we are going to do it. We take a free abelian group on Q. So we take the free ordered groupoid on Q. This construction is a little bit subtle. For groups, we look at free groups on a set, but for ordered groupoids, we look at free ordered groupoids on the underlying graphs. So we take Q, take the underlying graph, and then look at the free ordered groupoid on this underlying graph. And we denote the kernel of this map. So every object in this free ordered groupoid can be identified with something in Q. If you have, so the free ordered groupoid will have paths instead of having strings of words for groups. Here you have paths, and each path we can associate, we can identify it with its corresponding image in Q by just looking at the composite of the individual elements in Q, the individual morphisms in Q. So the kernel of this map you denote by Q. If you want to know more about free ordered groupoids, you can check the paper by Benjamin Steinbeck with title Factorization Theorem for Morphisms of Ordered Groupoids and Inverse Semigroups. It gives a very clear and interesting, comprehensible account of free ordered groupoids on underlying graphs, and together with actions of ordered groupoids. So we note that we can form the free ordered groupoids, and we are denoting the kernel of this map by n. So we can form, if you have a Q module A, then we can form the semi-direct products of FQ by A. So there is this FQ shouldn't be there. So we can form the semi-direct product FQ cross A, because FQ will also act on A via.
Sorry, Bernard.
Phi. Yes, please.
I beg your pardon on FQ. What is FQ again?
FQ is a free ordered groupoid on the underlying graph of Q.
Oh, yeah, understood. Okay, thank you.
Yeah, the free ordered groupoid. You're most welcome. So FQ is a free ordered groupoid on the underlying graph of Q. And so if you have a Q module A, that is also going to be an FQ module, because FQ can act on it via pi. So we can form the semi-direct products, and then the kernel NQ is going to also act on A by conjugation. FQ is acting, so the kernel is also going to act by conjugation, again via pi. So we can look at morphisms from NQ into A that will respect the Q action, the FQ action. And we form these sets, M phi, where phi is supposed to be an ordered functor from NQ into A that respects the FQ action. Now it is this guy here that will help us to be able to build extensions, equivalent classes of extensions that are going to be in correspondence with the objects that we have there. So this is what we observed, that the quotient of the semi-direct product S, semi-direct product FQ by A by M phi, is an extension of A by Q. And so we notice that every extension that you have, every extension of the ordered groupoid A by Q is actually equivalent to some extension E alpha, where alpha is supposed to be a map, an ordered morphism from NQ into A that respects the FQ action. So this extension here can be identified with something here, E alpha. And in fact, it turns out that any two of these maps, any two of these extensions, E phi, E psi, will be equivalent if and only if it is a restriction of an ordered derivative. There is a feedback from somewhere. Okay, so we can say that E phi and E psi are equivalent if and only if their difference is a restriction of an ordered derivation from FQ into A. And so the set of equivalent classes of extensions of this nature is in correspondence with all ordered functors from NQ into A. And so we can identify all the equivalent classes of extensions of ordered groupoids, A by Q, with this object here, which is just all ordered functors from N into A that respect the Q action, which is the same as respecting the FQ action. And so based on that, we can state the main theorem that says that the set of equivalent classes of extensions of the ordered groupoid A by Q is in one-to-one correspondence with the second cohomology group, H2 of Qi with coefficient in A0, and not just Q with coefficient in A. And the isomorphism is obtained from the fact that this object here is 0. It's trivial because A0 is going to be injective and higher cohomology groups will vanish. The proof is shown in the paper on extensions and cohomology of ordered groupoids that we published out there. So we show that this is 0, this is trivial, and then we have just seen that the map, the co-kernel here, is just going to give us an isomorphism between these two groups. So we can say that the set of equivalent classes of extensions of ordered groupoids of A by Q is in one-to-one correspondence with this second cohomology group. And that is how we classify extensions of ordered groupoids. Thank you. In Ghana, we will say that.